This is the lecture on the central limit theorem. So we're kind of moving from the part in the course where we just describe statistics into how we make inferences based on statistics. So you have a little bit of a break from R this week. We're talking theory related to statistics. If I were you, I'd spend my time preparing your literature review, making sure you're finding sources, so you have a little bit of a break of a homework on that. Okay, so to understand what's going on here, you have to understand the properties of the normal distribution. Based on the properties of the normal distribution, we can figure out the probability of something occurring. So I'm just going to show it to you as a picture because it's easier to explain these properties with this picture. So you see here in figure 8.1, you know, they used to have this thing where I could like draw a picture. Yeah, here we go. Oh, you see this? Perfect. So hopefully you can see some of this stuff because I've noticed on some of my last things you can't see it. Okay, so the people will frequently refer to anything that has this bell-shaped thing. They'll call that a normal distribution. But it's important for you to remember that the normal distribution has three properties, and unless it has all three of those properties, it's not a normal distribution, even though it might have kind of a bell-looking shape to it. The first is that it's symmetrical, that there are as many observations on this side as there are on this side, and there's some symmetry to it. Also, the mean, median, and mode all equal each other. They're the same value. And it has an asymptotic tail, which is a mathematical term for saying that these values will get closer and closer to the x-axis, but the values never touch the x-axis. It's infinite on both sides, the normal distribution. So things can be distributed in a normal kind of fashion, right? In height, you've got some people that are super tall. You've got some people that are super short. But these actually aren't technically normally distributed because there's not an infinite height. It ends at some point, and there's not infinitely short, right? At some point, there's a 0 point where a person doesn't measure any height at all. In fact, I can't imagine what a person looks like who's at a 0 height. So even babies, as they're born, have some height. So it's not technically normally distributed, but it looks kind of bell-shaped, and so people will talk about that height is normally distributed, or intelligence, depending on how you measure it. IQ scores are forced to be normally distributed, so you could talk about some kind of a normal distribution in intelligence. But again, there's not negative intelligence, right? So there is an end to those things. So there's not an asymptotic tail on most things, but some things, many things, tend to be kind of like this bell shape in the distribution. Most people score in the middle on some trait, with very few people on the high end and very few people on the low end. So if we know something, the properties of the normal distribution are that I'll show you again in this picture because it's easier to see. Almost 100% of the values lie within 3 standard deviations of the mean. All right, so whatever this is, let's just say it's IQ scores. The mean is 100. Then you can score 110, 120, 130, right? You could convert that into standard deviation scores where the mean would be a 0, and 110 would be 1 standard deviation above the mean, and 120 is 2 standard deviations above the mean, and so on. And you could also do the same on the negative side. You could score it into standard deviation scores, and you could look at how a person fits in terms of standard deviations above and below the mean. This is basically what standardized testing does. Standardized testing takes your score, converts it into some kind of a standard deviation score, and then tells you how you perform relative to everybody else. That's why on an ACT test, you never know how many you missed, because what they're doing is they're taking how many you got right, how many you got wrong, and converting that into a standardized score, a standard deviation score, so that 95% of everybody fits within 3 standard deviations of the mean. So if we know that something is normally distributed, we also know something about how those cases lie. So you only get 0.13% of the population that scores above 3 standard deviations of the mean, or scores below 3 standard deviations of the mean. Right, so this is why if you get a 36, I think it is, on your ACT, they just call it a perfect score, because 36 is 3 standard deviations above the mean on the ACT. Very, very few people score higher than that, and so they just stop it there, right? They're not like, well, you're at 36.2. They just leave it there. They say, great, you're in that small category of people that does better than perfect, but we'll just call you perfect. And then there's like a low score to the ACT, right? There's the bottom. And there's so few people that fit in there that they don't put it in there, include it in the score. So you've got 100% minus 0.26%, so you got like 99.7% basically, fits within 3 standard deviations of the mean on a normal distribution. So these tables say the same thing that I'm just telling you. So that's kind of nice when you're trying to make predictions about things that happen in life. You can just take something, you can convert it to standard deviation scores, you can, or as we say it in common vernacular, standardize it, and then you can talk about the probability of something occurring. The problem is that some things in life aren't normally distributed. So this is where the central limit theorem comes in. Right? Sometimes you'll standardize scores and you'll get things 4 standard deviations below the mean, even though you've normalized, right? And you'll get things that are like only 2 standard deviations above the mean is the maximum score. Something like income, right? If you're measuring income in the amount of dollars one earns per year, that's not normally distributed. There are a lot more people at the low end of the income scale than there are at the high end of the income scale. And so it looks kind of like this. Income is distributed like this, like whoa, and then down, and then flattens out really low. Because the uber wealthy people in the world don't earn income. They own things, right? So there are a zero income a lot of people, so it just kind of goes like that, right? And that's not normally distributed. So if this right here is a picture, I used R and I said, give me a random sample of numbers and make them normally distributed. And this is what R gave me. That looks pretty close to normal, right? Although my mean, it looks like is 5 instead of 0, but whatever. There's my normal, yeah, my mean's 5.418. Okay, but this right here, the black line is the actual normal distribution. And then this dotted line is my fake normal distribution that I got made for me out of R. And you can see from this that even R, when you ask computer software to simulate normal data, can't get it exactly right. And so you might say to yourself, well, if even a computer program can't simulate data that's exactly normally distributed, maybe nothing's normal. That could be like an existential question for all of us. Are any of us normal? What is normal? But don't worry, the central limit theorem helps us out. It says that it doesn't matter if your data are normally distributed. For any distribution of X, that means for any column of observations you have, right? No matter what you're measuring out there, the value associated with a large number of independent observations, so like a mean or a standard deviation, is normally distributed, sometimes a correlation. And as the number of observations increases, that distribution becomes normal. So what this is saying is, that's right, maybe like whatever you're interested in isn't normally distributed. Gender, right? It doesn't make any sense that gender would be normally distributed. Or biological sex, right? You're going to have some males, you're going to have some females, you're going to have some in-betweens, you're going to have some nones, but it certainly is not going to look like a normal distribution, especially since sex isn't a number, so you can't even put it in a normal distribution. But you might say that's not normally distributed. But what the central limit theorem says is that the means of those values are normally distributed. So as long as what we're interested in is something like a mean, then we can assume normality. So this becomes really important for us. If we were in a math class, I would just show you the equation, and then I would do the proof of the equation, and then you would all say, oh, that's awesome, now I get it. But since most of you have chosen to do political science or public policy because you want to avoid math and hope to never deal with numbers again in the rest of your life, I'll do a little simulation example so you can see what's happening. And then it'll have as powerful effect on your minds as if I had done a mathematical proof. Especially because somewhere in the middle of the mathematical proof, I would forget basic algebra skills and I'd be like, what do we do? Well, we squared it, right? Oh man, I'm lost. So that would just confuse you more. All right, so here I have a simulation from R. What I did is I took 50 observations from a binomial distribution. What that means is you like flip a coin, and if it's heads, you give it a 1. If it's tails, you give it a 0. Then you do it again. Heads is 1, tails is 0. So I did this 50 times, and I got about 15 heads and about 35 tails. Now you look at this and you say, that's not normally distributed. That's just a bunch of 1s and 0s. That's right. But what I'm doing is I'm taking the mean of this. So I'm going to take that mean and I'm going to put it in another column of data. I'm going to do it again, another 50 times. And I get, this time, what is it like, 14 heads and like 36 tails. Here's my mean, 28. Then I do it again, flipping the coins a bunch of times. This seems to be a very weighted coin, right? Because this time I got less than 10 heads and 41 tails. It seems to be in favor of tails. Probably because when I was doing the programming thing, I didn't do it just right. Actually, back when I was an undergrad learning statistics, my professor made me actually flip a coin and then create these columns of data so that I could see it and then take the means of it. So you should feel happy. I'm not making you spend hours at home flipping coins, taking the means of your data, and then putting that in another column to prove the central limit theorem to yourself. We're using computer simulations in R to see how it works. Anyhow, this one's mean is 0.18. Then I do it again. Oh, this one had a few more heads, but we're still not even to 20 heads. Well, it means 0.36. When I just do it over and over and over again. So if I were to do that many, many times, what do you think the distribution of the means would look like? Well, so far I've done it 4 times, right? If I were to do it 100 times, so that's actually a total of 5,000 coin flips, right? So I'm flipping the coin 50 times, recording heads and tails, taking the mean, that's 1 time. I do it 100 times, you see what the distribution starts to look like. At least it's not binomial anymore, but it doesn't really look normal. If I do it 2,000, I get some extreme values out here, but still it doesn't even look like a bell exactly, maybe a little bit. I do it 100,000 times and you see how it's starting to look like a normal distribution. I actually simulated it 1,000,000 times, but it took about 10 minutes for R to run the program, and I forgot to save the picture. But you can just believe me, at 1,000,000 times, it looks exactly like a normal distribution. So what this is showing you is that the central limit theorem works. Even if you take a weighted coin that doesn't even flip heads and tails exactly right each time, even something that's like not just binomial, but poorly binomial distributed, as long as all you're interested in is the means, if you do that over and over and over again, you're going to get something that looks like a normal distribution. You see that the mean ends up being 0.3, right? This is the proportion of times that I get a tails to a heads, right? So it still recognizes that it's a weighted coin, because if it was not a weighted, then my proportion here should be 0.5. So it catches that, but it doesn't matter, it still looks normally distributed. So what we do in inferential statistics is we collect some data, get a sample of some kind. We assume that the mean of whatever it is we collected is going to be normally distributed. So then we take the mean from our sample, we convert it into a standard deviation score, and then we say, what's the probability of there being nothing? And then I would get a mean like this from this random sample of the population. That's basically what statistics is. I know that what I just explained is a little bit beyond what you're ready for, but this is why the central limit theorem matters to us. So no matter what the distribution actually looks like, the mean of that is normally distributed. This is another paragraph that says exactly the same things in different words. Because sometimes I just try to repeat myself because I say, if I say it in enough times in different words slightly, then maybe it'll make sense to everybody. So this is what we do. Take a score, take a sample of some kind, right? Take the mean of that, normalize it, and then say, what's the probability of getting that score? So the z-score is an example of a standardized score that you could use. And the way that you calculate a z-score is you take your raw score, subtract from that the mean of your sample, and divide it by the standard deviation of your sample. Super easy. Every time you take a standardized test, this is exactly what they're doing to tell you how good you are. So we'll have some fun with this to kind of help you make sure that you understand the concept. So the IQ test has a mean of 100 and a standard deviation of 10. And you score a 120. How many standard deviations above or below the mean is your score? These are your options. So I'll go back to this so that you can look at the equation and plug the numbers in. I don't like to do complicated math in my head, so I made it super easy for you. So you should maybe pause the video and figure it out. Otherwise, you'll just hear the answer and won't learn anything. So how many standard deviations above or below the mean is your score? 2 is the answer. 120 minus 100 divided by 10 is 2. Okay, here's a little bit. This is actually real about the LSAT. So many of you who want to be lawyers. The LSAT has a mean of 150 and a standard deviation of 10. So if you get a 160 on the LSAT, what percent of LSAT test takers did worse than you? So you have to like convert this into your standard deviation score. And then you have to come back to this chart right here, there. So if you know where you're at in terms of standard deviation scores, then you'll know exactly how many people did worse than you. Right, so if you get a 150 on the LSAT, and you know that you're at the 0 point, that's the mean. So this plus this plus this plus this is how many did worse than you. If you get a 160 on the LSAT, this plus this plus this plus this plus this did worse than you. What does that put you in, like the 75th percentile? Maybe the 85th. That plus that plus that. That's around 15% do better than you, right? If you get a 160. So you say, I want to go to BYU Law. Okay, they probably want you to get around a 161, 165, maybe something like that. So they want you in the top 10%, I would say, right? A 165 puts you right in here. So they want you in the top 10% of LSAT test takers. I've had plenty of students ask me for a letter of recommendation, and they get an LSAT of 150 or less, right? So they're somewhere in this range here. And it's like I feel like I have to explain to the people, right? You should let so-and-so in your law school, even though half of the people that took the test did better than this person. I say stuff like, the LSAT doesn't tell you about all of their fine qualities, like so-and-so smiles all the time, and it makes me feel so happy inside. Or so-and-so really loves Jesus. And maybe that's a reason you should let them into your law school. But typically what happens is if you get an LSAT score in this range, all the law schools say, no, thank you, we're not interested. In fact, if you get below a 160, most law schools will tell you they're not interested in you. So the advice I typically give people is if you're like a 155 or lower on the LSAT, don't waste your time. Because what law school wants to be so proud of we take people that are below the mean. We take people that are just about average in America. They don't want to advertise that. So you end up going to a very expensive law school that doesn't have a good reputation. All right, the last one we'll kind of play with. All right, let's say you get a 170 on the LSAT. What percent of LSAT test takers did worse than you? Again, we go back to this. And 170 puts you 2 standard deviations above the mean. So 2.5% do better than you. So that puts you in like the 97.5 percentile, right? So if you look up like LSAT scores, you need to get into Stanford or Harvard or something like that. They want you above 170 to get into their law schools. So frequently we talk about how representative the Supreme Court is, and because there's some gender diversity on there and there's some racial diversity on there. But you know what thing Supreme Court justices all have in common? They all went to law school at either Harvard or Yale. I don't think there's even any of them that went to Stanford. So that means, by definition, that all of them are unusual, because that means they all scored at one point on the LSAT in this range up here, which makes them unusual. Only 2.5% did better than them on the LSAT. So in some ways, maybe they're diverse, and in some ways, maybe they are representative of America, or maybe somehow they understand what it's like for the rest of America. But one of my biggest gripes about how much people care about what the Supreme Court thinks about things is the fact that so many of the people on this, virtually all of the people on the Supreme Court, although we can't look up their LSAT scores, based on where they went to law school, we can assume that they had LSAT scores in this range. And that gives you a particular set of skills, but also means you're probably different than other people. You probably see the world in different ways, or at least there's some ways that you're unusual. So I can say that not as like a mean thing to say about Supreme Court justices, but just as a matter of fact, right? Supreme Court justices score 2 standard deviations above the mean on the LSAT, makes them unusual statistically. Okay, so that's the central limit theorem. It's going to be important for the things we do in class going forward, but I understand if right now all of your attention and all of your focus and all of your everything is on getting that literature review done. That's the way it ought to be. I wish you luck. I hope you have a great time. That's all.